In this video, we'll be doing some example problems regarding unit cell volume, APF, that is atomic packing factor, theoretical density, and percentage crystallinity. So let's begin. In the first problem, we have to determine the unit cell volume of an FCC crystal structure. So it says that calculate the volume of an FCC unit cell in terms of the atomic radius. So we have to find here a relation of the atomic volume of an FCC unit cell in terms of its atomic radius. Okay, so we can see that this this height and this length, and that is also equal to this breadth, all have the same dimensions, that is a, the edge length, or you can say that these are the lattice constants or lattice parameters. So we have to find this in terms of the radius. So calculating this edge length here in terms of r, so you can see that this is a right angle triangle, and we can find out from this right angle triangle, we can see that this perpendicular square plus base square would be equal to the hypotenuse square, which is 4r, 4r square. So how this is 4r? So we know that this has one radius, r. This atom's radius is r, and this is what, that is the diameter of the atom. So in totality it is 4r. So solving out this, we can solve it as 2a square would be equal to 16 r square. So we'll be taking the roots on both sides and simplifying it. So we'll be getting that is constant as a is equals to 2r root. So this is the value of the lattice constant. So now we know that the volume of a cube is the a cube, that is this side to this side to this side, all these sides are equal. The volume is a cube. So putting this edge length, we'll be getting 16 r cube root. So this is a unit cell volume of an FCC crystal structure. Next, we have to computate the atomic packing factor for an FCC crystal structure unit cell. So in this, it says show that the atomic packing factor for an FCC crystal structure is 0.74. So we have to prove that the APF of an FCC is 74% or 0.74. So the formula for APF is the volume of atoms in a unit cell divided by the total unit cell volume. So we calculated the total unit cell volume in the previous problem as 16 r cube root 2. So we'll be taking VC as 16 r cube root 2, as you can see over here. The volume of atoms in a unit cell, VF. So we have to calculate the volume of this. So we know that in an FCC crystal structure we have 4 atoms, okay, and these atoms are spherical. So the volume of sphere is basically 4 upon 3 pi r cube. So we'll be multiplying it by 4 because we have 4 atoms over here. So we'll be taking the volume of 4 atoms, that is 16 upon 3 pi r cube. So now we have this volume of atoms in a unit cell, that is 16 upon 3 pi r cube, which would be less than the total volume of the unit cell, since it has empty spaces as well. So we'll be dividing the volume of the atoms with the total volume, this, and we'll be cancelling this r cube and r cube. 16 and 16 will be cancelled out as well. So solving this pi upon 3 divided by root 2, we will be getting 0.74. So this is the atomic packing factor for an FCC crystal structure unit cell. So now we'll be calculating some theoretical densities. So the formula of theoretical density is basically the density is mass over the volume. So for mass over here it is given n multiplied by a. N is the number of atoms in the unit cell. A is the atomic weight, and n is the Avogadro's number. So this total is the when we solve this, we'll be getting this mass that is in grams per mole, and C is the volume of the unit cell. So this mass on total volume. Okay, so let's start the example. So we have given the atomic radius and crystal structures of some elements, which we also discussed in the previous video. So now we have to find out the critical density for copper. So in the question it is given that copper has an atomic radius of 0.128 nanometers. Nano is 10 to the power minus 9. It is also given in the slide as copper. You can see that this is 0.178. In the problems given in the exam, you will be given the chart plot, the exact value of this. So here we have the atomic radius as 0.128 nanometers, and this has a crystal structure of FCC, which we know that it has 4 atoms. So it would be a BCC crystal structure. We'd be having 2 atoms over here. So, and the atomic weight in gram per mole of copper is 63.5, which can be calculated from which can be extracted from the periodic table. So it says calculate its theoretical density and compare the answer with the measured densities. The measured density given of copper is 8.94 gram per centimeter cube. You can find out from the internet or any other resource. So this is the experimental value, and the theoretical value we'll be calculating. So and we know that it has 4 atoms. The A of copper is 63.5, which is given in the question. Vc is the volume of the copper crystal structure cell. So since we know that it's an FCC, then we'll be using this formula, that is 16R2, which we did in question 1. And R we have over here is 0.128 nanometers, and Na is the Avogadro's number. We will be putting the values inside, and the answer is 8.89, which is approximately equal to the actual density of copper. So we can say that our answer is around correct. Okay. So let's now calculate the percentage crystallinity. So in a polymeric material, we usually find this percentage crystallinity, that how much amount of polymer is crystalline and how much of that is amorphous. So you know that rho C is the density of a perfectly crystalline region, and rho S is the density of a the total density of the specimen. So A is the density of the perfectly amorphous polymer, the amorphous part of the polymer. So here is a question of polyethylene, in which we have to find the density and the percentage crystallinity of a polyethylene polymer. So we have 2 parts in the question. First is to compute the density of totally crystalline polyethylene. It has an orthorhombic unit cell. It does not have a cubic unit cell. So all these sides are not equal. You can see that all the sides are unequal, but the angles are at 90 degrees. So, and each unit has two ethylene units. Okay, so each unit cell has two ethylene units. So we'll be multiplying by 2 as well. The number of atoms per unit cell is 2, which is given in the question. Okay, so first let's do this part A, and then we'll come to the part B. So here you know that the formula for density is again rho is equals to Na upon Vc. N is the number of atoms. A is the atomic weight in grams per mole. Vc is the volume, and Na is the Avogadro's number. So first of all, the number of atoms, we have this formula. N is 2. Each atom has 2 repeating units, so we'll be taking the number of atoms as 2. So now this A, so we have to calculate this A. We know that the formula of hydrogen is like this. It has 2 carbons and there's 4 hydrogens, something like this, and the 2 bonds are open from this side, which make the polymer. So it has 2 carbons, so we take each carbon has a mass of 12.01 gram per mole. So we'll be multiplying by 2, and we have 4 hydrogens which has a mass of 1.08, and they are 4 hydrogen atoms. So we'll be adding the total mass, and the total mass will be 28.05. So we'll be putting A as 28.05. Now for volume, we'll be multiplying all these sides. Note that sides are in nanometers, and we'll be taking the volume in meters, so or centimeters. So we'll be taking this 10 power minus 8. We'll be converting the nano into centimeters. So we'll be multiplying all the sides to get the volume. So we have the number of atoms, we have the atomic weight, have the volume of the unit cell, and we have the Avogadro's number. So we'll be solving it out, and we get this answer as 0.998 grams per cell. So this is the theoretical density of the orthorhombic polyethylene unit cell. So now let's get back to the part B. It says, using the answer to part A, calculate the percentage crystallinity of a branched polyethylene that has a density of 0.925 grams per centimeter. The density for the total amorphous material is 0.887. You can see that the density of the amorphous part is lesser than that of the crystalline part. So we have our formula over here, in which we have those as 0.998, which we calculated in the previous question. This is the density of the crystalline part, and the density of the amorphous part is 0.874, which is given in the question, as well as the density of the specimen part is 0.925 grams per centimeter cube, which is also given in the question. So we'll be putting the values in this, and here we find the percentage crystallinity as 46.4. So the other 53.6% would be amorphous. So the polyethylene polymer, you can say, is that half of it is around amorphous, and it is less than half of that is crystalline and the crystalline structure. Okay. So that was it. Thank you.